Partial orders are another way to talk about digraphs, and they offer to us an interesting lesson in the idea of axiomatizing a mathematical structure and mathematical ideas. So let's begin by discussing some of the properties that we're going to use to axiomatize partial orders and digraphs. So if we think about walks in a digraph, the basic property of walks is that if you have a walk from U to V and you have a walk from V to W, then you put the two walks together and you wind up with a walk from U to W. Expressed in terms of the positive walk relation in G, what this is saying is that if U G plus V and V G plus W, then U G plus W. And that abstract property, which I'm highlighting with the magenta box, when you apply it to an arbitrary relation, is called the transitivity property. So a relation R on a set, that is R is relating the domain and codomain of R are the same, is that URV and VRW implies URW. And a relation that has that property is said to be transitive. And of course, what we've just seen is that the positive path relation of any graph G is transitive. Another way to say transitivity is to read URV as saying there's an edge from U to V. And what this says is that if there's an edge from U to V and an edge from V to W, there's an edge from U to W. Or in other words, if there's a path of length 2, there's a path of length 1. And then by easy induction, it follows that if there's a path of any length, of any positive length between two vertices, then in fact there's a path of length 1, that is an edge between them. Okay, so the basic theorem that we have to begin with is what is transitivity capturing as a property of a relation, and a relation R is transitive if and only if, in fact, R is equal to the positive walk relation for some digraph G. The proof of this is basically trivial because you can let the relation R be the digraph that it's the positive path relation of. If we look now at directed acyclic graphs, then what we have is that if there's a positive length path from a vertex U to a vertex V, then since there's no cycles in a directed acyclic graph, there can't be a path back from V to U. And that property is called asymmetry. So D plus, which is the positive path relation, in a DAG has this asymmetry property, namely, if U can get to V by a positive length path, then it's not possible for V to get back to U by a positive length path. So abstracted URV implies not VRU. That's the asymmetry property of an arbitrary relation R, and by definition of acyclic, D plus is asymmetric in a graph without cycles. Okay. A strict partial order is simply a relation that has these two properties of being transitive and asymmetric. And some examples of strict partial orders are the proper containment relation on sets, which we've previously commented can be viewed as a DAG, but now it satisfies transitivity, and the fact that if one set's properly contained in another, the second one can't be properly contained in the first, because proper means you have something extra. The indirect prerequisite relation on MIT subjects would be another example of a strict prerequisite. If I'm a prerequisite of you, you can't be a prerequisite of me. And finally, the less than relation on real numbers. These are all examples of strict partial orders. And putting together the previous reasoning, what we can say is that a relation R is a strict partial order if and only if R is the positive path relation for some deg D. So the axioms that define strict partial order, namely transitivity and asymmetry, can be said to abstractly capture the property of a relation that it comes from a DAG. Another important property of partial orders is the idea of being path total, or linear, as some authors call it. And the simple definition of path total is that given any two elements, one is going to be bigger than the other with respect to the relation.
Hello everybody, welcome back to Discrete Mathematics. Today we're going to take a look at equivalence relations and partial orders. So last video at the end I briefly mentioned what an equivalence relation was. It is a relation that is reflexive, symmetric, and transitive. So just to review what this means, for reflexivity, for any element A, we have that A is related to A. So what this looks like with a point is we get a loop. So A would be related to A. For symmetry, if we have points A and B, then if A is related to B, we expect B to be related to A. So if we have 2 points on a graph here, then if we have an arrow pointing from one to the other, we get another arrow pointing back. The third one is transitive. So this means if A is related to B and B is related to C, then we're going to get that A is related to C. So we have 3 points here, and we have an arrow from A to B, we have an arrow from B to C, therefore we're going to get this arrow from A to C. So when we put the three together, let's say we have 3 elements, so put the 3 together, let's say we have 3 elements, so we have these 3 here. Well, they all have to be related to themselves, so we get some nice reflexive arrows here. And let's say that A, we're going to have 12 back, and B points to C, then we should get Z thing. And basically what this says is that all of the elements are equal to each other. So a good equivalence relation is the equal sign. So A is equal to B is equal to C. So 1 is equal to 1 is equal to 1. This satisfies all 3 conditions, but we've already talked about that, so let's go on to denoting equivalence relations with notation. Equivalence relations, this here. Put the 3 together. Let's say we have 3 elements, so we have so it's 5 right relations, but we've already talked about that, so let's go on to this satisfies all 3 conditions, but we've already talked about. about that. So R, and so we can write an equivalence relation R as this sort of box X. So we say X in square brackets, and it's equal to the set of Y such that X is related to Y. So what this means here is if we have some element A, we have another element B, then the equivalence relation on this element A here is everything that's related to B. So let's call this box A, for instance, and we say that A is related to Y, or sorry, A is related to B. This means that this is just the set B. So this might be a little bit confusing, but these 2 points coming up next are going to hopefully clear it up a little bit. First point is either the equivalence relation on X can be equal to another equivalence relation Y, or the intersection of them can be empty. So basically what this means is, let's say if we have A is related to B and C is related to B, well, then we have this condition here where the equivalence relation of A is going to be the same thing as the equivalence relation of C. But let's say A is related to B and C is going to be related to D, and we know that A is not related to D. This means that C cannot be related to B if we have an equivalence relation, because their intersection must be empty. So you don't normally see this notation used too much outside of modular arithmetic, so when we do that, we're going to touch on this notation again a bit, but it's a good idea to introduce it now just to get it into your minds. So we need to introduce a new type of relation, and that is the relation of anti-symmetry. Now, when you see the word anti, you sort of think of the word not, and we should not do that with anti-symmetry because the definition's a little bit more confusing. So what this says is that if A is related to B and B is related to A, then A is going to be equal to B. So what this means is that if two objects are related to each other, they're going to be the same object in an anti-symmetric relation. So for instance, we have this less than or equals to sign operator. So if we have the case where X is less than or equal to Y, and we have the case where Y is less than or equal to X, then we're going to get that X is equal to Y, because that's the only way that these two values are going to make any sense. X has to be equal to Y. And another operator we can show this with is the subset relation. So if we have A as a subset of B, and we have B, sort of think of the word not. And we should not do that with anti-symmetry because the definition's a little bit more confusing. So what this says is that if A is related to B and B is related to A, then A is going to be equal to B. So what this means is that if two objects are related to each other, they're going to be the same object in an anti-symmetric relation. So for instance, we have this less than or equals to sign operator. So if we have the case where X is less than or equal to Y, and we have the case where y is less than or equal to x, then we're going to get that x is equal to y. Because that's the only way that these two values are going to make any sense. X has to be equal to y. And another operator we can show this with is the subset relation. So if we have A as a subset of B, and we have B is a subset of A, then we know that the sets A and B are equal to each other by definition, because all of A is contained within B, and all of B is contained within A, therefore they must both be equal. So this is the anti-symmetric property. And we're going to be using this in the case of partial orders. So partial orders, they are not an equivalence relation, but they're another type of relation that we should be familiar with. So partial order is going to be anti-symmetric. So no surprises there. If there was a surprise, well, I wouldn't have introduced anti-symmetry in the slide before this. It's going to be reflexive, and it's also going to be transitive. And with partial orders, what we can do is we can use this little symbol right here, sort of like a less than or equals to sign with like a little tail sticking out. Not really, but we can use that to denote a partial order. And basically, what we get with a partial order is we don't get the case where if we have two elements, they go back and forth. We don't get this property. Instead, what we get is this sort of property. And I'm going to hold off on that sort of explanation for just a second here. And we're going to talk about some types of partial orders, because I think it's good to do this before we get into how we show them graphically and how we talk about them. So here's a couple types of partial orders. We have x less than or equal to y. So this is sort of true. Well, it is true. Completely true. Suppose we have, say, 2 less than or equal to 4. Well, it's reflexive, and so for instance we have 2 less than or equal to 2. This is going to be true for any element. It's transitive, because if we say have a 2 less than or equal to 4, and we have 4 less than or equal to 5, then we know that 2 is going to be less than or equal to 5. And it's anti-symmetric, because if we have 3 is less than or equal to 3, or let's just say more generally x is less than or equal to y, and y is less than or equal to x, then we're going to get x is equal to y. So that's a partial order. Alphabetical order, it's a little bit more interesting, but it's basically the same system as the x less than or equal to y order. Instead of looking at values of numbers, we just take the letters in alphabetical order. So we know that a is going to be less than or equal to a if we order it like A, B, C, and we call that an ordered pair, and that's the whole alphabet, goes down to Z. Then we know that A is going to be less than or equal to the position of A if A is before B and B is before C, then we know A is before C. And if some letter X is before the letter Y, or at its position, and Y is before or at position X, then that means that X must be the same thing as Y. So it's a little bit more abstract there, but we can write this using our notation as A is in a poset or posit with respect to B, C, so on and so forth. So we can show partial orders like this. Now, a good way to represent partial orders is with Hasse diagrams or Hasse diagrams. So we have a set here 1, 2, 3, 4, and we've defined a relation where x is related to y if x divides y. So x exactly divides y. So if we take a look at our relation here, 1 divides 1, so you can put 1 into 1. 1 divides 2, you can put 1 into 2. 2 divides 2, because you can put 2 into 2. 2 divides 4 because you can put 2 into 4 twice, so on and so forth. So this is the relation we're going to look at. And we should probably check to see if it is a partial order. So let's take a look here. Is it reflexive? Well, we have 1, 1, 2, 2, 3, 3, and 4, 4. So we're good. Is it transitive? Okay, well, we have 1, 2, and 2, 4, so we should have 1, 4. Okay, we're good. And we have, I think that's really it we have to look for in transitivity. And then anti-symmetry. Basically, do we have two things that are symmetric to each other? We have 1, 2, we don't have 2, 1. We have 1, 3, we don't have 3, 1. We have 1, 4, we don't have 4, 1. 2, 4, we don't have 4, 2. So yeah, we're looking good here. And of course, symmetry is okay because we have 1, 1. So it's also going to be 1, 1. Because if we have 1, 1 and 1, 1, then 1 is equal to 1, which we know. So how do we represent this? Well, what we do is we give each element a point. So we'll call this 1. I'm going to put 2 over here, put 3 right here, and let's put 4 right up here. So we're going to draw some arrows with our relations here. So we know 1 goes to 1, so we'll put an arrow there. 1 goes to 2, 1 goes to 3, 1 goes to 4, 2 goes to 2, 3 goes to 3, 4 goes to 4, and we also know that 2 goes to 4. So we have this diagram here, and it's pretty messy. So we have these wonderful things called Hasse diagrams that make things look just a little bit nicer. So here's what we do. When we do a Hasse diagram, we say it's a partial order, since we only use Hasse diagrams for partial orders. So there's a few things we know. Let's just label these 1, 2, 3, and 4. We know in a partial order everything's going to be symmetric. So what we're going to do is just eliminate all of our reflexive arrows. We also know that in the case where 1 goes to 2 and 2 goes to 4, we're going to get this 1 goes to 4 by transitivity. So instead we're just going to say, well, we know it's going to be transitive, so let's just eliminate that line. We don't need that either. In fact, we're going to eliminate direction completely because we can figure out the direction it goes, and we know it's always going to be in the same direction due to the anti-symmetry property. So when we do all of that, we remove the reflexivity, we remove the transitivity, we remove the anti-symmetry from our diagram, we get something a little bit cleaner. And basically what this means is that we have, well, the same relations that occur over here. Just we've made it a little bit nicer. So if we have a path from 1, 2, and 4, this means that we have 1R2, 1R4. So if we connect something to a higher element, it's in a relation with everything it's connected to. So 1 is in a relation with 3, 2 is in a relation with 4, and it's always going to go up. You can draw them from top to bottom or bottom to top. It's good to specify which. General convention is that the lowest number goes on the bottom and it works bottom to top. So that's a Hasse diagram. It's kind of nice to look at. It's a little bit cleaner. Eliminating arrows is always a nice thing to do. So there's a very interesting type of Hasse diagram, and I'm going to demonstrate it with this set. If A is 1, 2, 4, and 8, and we're going to use the same relation that x are y's if x divides y. So what's interesting about this? Well, 1 divides 2, 1 divides 4, 1 divides 8. 2 divides 4, 2 divides 8, 4 divides 8. And of course they're all reflexive, we know that. So let's draw what this will look like. So I need to be pretty careful here, because we're going to do it without a Hasse diagram, and then we're going to do it with a Hasse diagram. So we'll do that. That should be a 4, and that should be an 8. So we know all of these are going to be reflexive, so we're going to have to draw some reflexivity in there. And 1 is going to go to 2, 2 is going to go to 4, 4 is going to go to 8. And we also know that 1 is going to divide 4, and 1 is going to divide 8. We know 2 is also going to divide 8, and it's going to be a little bit difficult to make this look good. So I'm going to put this in there, and 2 divides 8, and this looks like just a terrible mess. So let's reduce this to a Hasse diagram. Well, we get rid of reflexivity here, because it takes up a lot of space, it's kind of ugly. We're going to get rid of our directions on all of our arrows, because they're not necessary. And we're going to get rid of transitivity, because we know that all partial orders are transitive. So now we get this really nice diagram that is called a total order. Why is it a total order? Because we can arrange all of our elements in a straight line. If we can arrange all of our elements in a connected straight line, it's called a total order. And that means that the elements are all reflexive, anti-symmetric, and transitive with each other. So this holds the same relations as it would before, but it's much more concise, much easier to look at. And using this, we can find minimum elements, we can find maximum elements, we can find some other least elements, greatest elements, but we won't cover that. Essentially, minimum element is the bottom, maximum is the top, least and greatest. So what can happen is you can have two bottoms in some graphs. So we can have, say, two total orders as one partial order. It's not really called a total order, but then we'd have a difference between a least element and a minimum element, where, say, in this, if we started with a 0 and a 1 and two different things, we'd have the minimum element being a 0, but the least element would be the pair 1 and 0 because they're at the very bottom. That means that x must be the same thing as y. So x, it's the order, or let's just check to that sort of explanation equal to 5 y thing to the x and a. So probably check to see if it's true. That's really good to draw there. And has we did something going to be a little bit is that we have, well, this element in 3 from times we have. So and this there's a very interesting type of Hasse diagram, and I'm going to demonstrate it with this set. If A is 1, 2, that should be a 4 divide 4. If we can arrange all of
Welcome back. We are moving on to the last segment of this chapter, that's partial order and lattices. In this lecture, I'll be dealing with equivalence relation and how do we compare it with real life examples. Then we'll move on to the new type of relation called partial ordering and how do we represent them with Hasse diagrams. EDE. And there's a relation S which says sharing a room. A shares with B, B shares a room with C, and D shares a room with E. So what kind of relation is this? So let's try to analyze it. Let's test for reflexive property. A shares room with A. When a person is in a room, he is actually sharing with himself. Yeah, this is acceptable. How about symmetric? A shares a room with B. It also means that B shares the same room with A. This is also acceptable. How about transitive? So A shares a room with B and B shares a room with C. With this I could say A shares a room with C. This is also acceptable. So this is basically an equivalence relation. Let's represent this in the form of a picture. Let's say there are some rooms. With this data, let's fill these rooms. A sharing with B. So A and B are in one room. Then B sharing with C. That means C is also belong to this particular room. D sharing with E. And these two are not sharing with the other guys. So obviously they have to be in the other room. We already know that equivalence relation basically creates partition. And these are the equivalence classes. And what it signifies is all the elements belonging to a particular class hold the same property. Or we can highlight the fact that equivalence relation can be thought as having equality or same property. Let me give you another example related to equivalence relation. Let's say you entered the college and the professor asks you, how did you come to college? And probably your answer is, I took bus 82 from home. Now think, is there only one particular bus with number 82? No, there could be many. Probably some 82M or 82L or 82K. There would be n number of buses which are moving in the route your home to college. Do you agree? Yep. Or maybe you want to travel from your home to a theater. Here you might pick up another bus, maybe some 36L or 36K or 36M, right? So if I think the set of buses, some 82M and 36L and so on, if this is the main set, probably we can define a relation root, which is an equivalence relation on this set, which partitions the set into subsets where each becomes an equivalence class. What it signifies is you can take any bus in this particular set to complete this task of coming from home to college. And we're not really worried whether you are taking M or L or K. We're only worried whether you are able to complete the task or not. Since each of these elements can equally perform this task, this forms an equivalence class for this particular relation root. So equivalence relation highlights the concept of equality in elements of set. But do you think that every problem in this universe can be solved with equality? No, not always. A simple example is taller an equivalence relation? Let's check. Think of symmetric property. A is taller than B. Does it imply B taller than A? No, it cannot be. If A is taller than B, then B must be short compared to A. Therefore, this does not hold. So taller cannot be classified as a equivalence relation. So there should be some other mechanism to handle these kind of things. Now this leads to a new concept called ordering, where a relation holds from A to B but does not hold from B to A. In this ordering, we talk about partial order and total order. So let's get started. Partial order. A relation which satisfies reflexive, anti-symmetric, and transitive. Reflexive is, for every element, there is a relation onto itself. Antisymmetric is A has a relation to B not equal to B relation A. Transitive, A relates to B and B relates to C implies that A relates to C. Let's say the relation here is P, and we're going to use the symbol greater than or equal to represent the partial order. Now, why specifically this is, this less than basically highlights the fact that the relation can be only unidirectional. It's either A to B or B to A, but it cannot be on both sides. And this equality highlights that there is a reflexive relation A to A. Let's take an example to understand this. Here we have a set people A, B and C, and the relation we are defining is not rich. A is not richer than B and A is not richer than C. Does this relation P form a partial order? Let's check. First is reflexive. A not rich than itself. Is it right? Yeah. Then antisymmetric. A not richer than B. So it is obvious that the other way around is not possible. B has to be richer than A. So even antisymmetric is accepted. How about transitive? Let's say that A not richer than B and B is not richer than some D. So obviously A is definitely not richer than D. So even transitive property can be accepted on this. Therefore, this is actually a partial order. We can draw a graph for this partial order with these elements as the nodes. So we have A, then B and C. Because it follows a reflexive property, each will have a self loop. Then the relation defined is A not richer than B, then A is not richer than C. And it's obvious the other way around is not possible. There are two observations. Every node will have a self loop and the graph will be unidirectional, right? So this diagram can be simplified. First thing is we will use dots for the nodes. So we have A, then B, then C. Because it's a partial order, it is understood that there will be a self loop. So let's ignore that. Then because there's a relation from A to B, we take this particular element has higher order and this of lower order. So we put this down and this in the top. And we draw a line. And we do not put any arrow because we already know that the relation is from bottom to top. So therefore relation should be A not rich than B. Similarly A not rich than C. So I could put another line this way. Here we have taken the convention of relation being from bottom to top. And this way of representation is called Hasse diagram. Let's take an example to understand how to draw an Hasse diagram. Here we have a set P, 3, 6, 18, 24 and 72. And there's a partial order defined such that A is a factor of B. Let's try to draw the Hasse diagram for this. First we pick up the first element, that is 3. So this will be the starting node. Now let's compare. So here the relation is factor. So is 3 a factor of 6? Yes, it is. So 6 has to be in the second level. And because the relation is there, we draw a line. Since the element 6 has satisfied the relation with 3, now we can make 6 as the base element for the further comparison. So let's take 6. Is 6 a factor of 18? Yes, it is. So 18 will be in the next level. Now the base element is 18. So when we compare with 24, so is 18 a factor of 24? No. So whenever the relation does not satisfy, we need to move one level back. So check with 6. Is 6 a factor of 24? Yes, it is. Therefore, we need to put this 24 above level 6. So I can put anywhere across. So I'll put it over here. 24. Now we have two elements as the base elements. So 18 and 24. So let's start with 18. Is 18 a factor of 72? Yes, it is. Therefore, I need to put it above this 72. We also need to check with 24. So 24, is it a factor of 72? Yes, it is. That's how we draw the Hasse diagram. Here there are few things to note with the Hasse diagram. If you pick up any node, let's say I pick up this node, all the nodes which are at lower level and that are connected to this will satisfy the property, which means that 3 will be a factor of 72, 6 will be a factor of 72, even 18 will be a factor of 72. All these elements satisfy the condition factor. How about 18? Only the lower elements will satisfy. So 6 and 3 will satisfy. The element which is above and at the same level, these two do not satisfy, which means 24 is not a factor and even 72 is a not factor for 18. Let's draw Hasse diagram for this as well. Here we have a set P, 2 do not satisfy. The element which is above and at the same level, these two do not satisfy, which means 24 is not a factor and even 72 is a not factor for 18. Let's draw Hasse diagram for this as well. Here we have a set P, 2, 4, 6, 8 and the partial order defined is A less than B. So let's start with the first node, that is 2. Compare it with the next element. Is 2 less than 4? Yes, it is. Now this is the base element. Compare it with the next element. Is 4 less than 6? Yes. How about 6 with 8? Yes, 6 is less than 8. So this is the Hasse diagram for this partial order. Do you see anything unique in this? Yes. Here each of the nodes are connected in a sequence and there are no branches. This type of connection is called as chain. There is one specialty for this. You see that every two elements can be compared. So if I take 2 and 4, 2 is less than 4. If I take 4 and 8, 4 is less than 8. Or if I take 4 and 6, 4 is less than 6. Any two elements can be compared. In a partial order, if every two elements can be compared, then that order is called as total order. If you look at the last example, this is not a total order because 18 and 24 are not comparable. Here's a question asked in GATE 1996. Let x 2, 3, 6, 12, 24, 36 and the relation less than or equal to b such that x less than y. If x divides y, draw the Hasse diagram of this partial order. Let's pick up the first node. That's 2. Then compare it. Does 2 divide 3? No, it does not. Therefore, put the 3 also in the same level, at the lowest level. So now we have two base elements. So let's check with the first element. Can 2 divide 6? Yes, it can. How about 3? 3 also can divide 6. Therefore, I need to put the element above this. So let me put it somewhere in between. 2 can divide 6 and even 3 can divide 6. Now this will be the base element. So can 6 divide 12? Yes. Then 12, can it divide 24? Yes. No, it cannot. So we move one step back. We need to put above 12. So becomes the Hasse diagram for this partial order. 36. So this becomes the Hasse diagram for this partial order. Here we have a set that is 2. Compare it with the function is called as partial order. This as well. So 6 and 3 will satisfy. The element which is above and at the same level, these two do not satisfy. Which means 24 is not a factor and even 72 is a not factor for 18. Let's draw 6 will be a factor of 72. Even 18 will be a factor of 72. All these elements satisfy the condition factor. How about 18? 3 will satisfy. The element which is above and at the same level, these two do not satisfy. Which means 24 is not a factor and even 72 is a not factor for 18. Let's draw